So today we're gonna talk about using differential energy balance and explaining um and derive the heat diffusion equation for energy balance for diffusion equation for cylindrical coordinate. So far we have been working with Cartesian coordinate which has X, Y, and Z. So they are all in length unit length. But for example, in a cylinder like this, we have the height and the arc length and the radius, but the arc length is made of from the angle in radian, which is not unit length. So in this case, we can have to use the different coordinate called radial or cylindrical, like the title coordinate, which ha which has. Let me just draw the Cartesian over here. Or actually, you can demonstrate the Cartesian coordinate on this cylinder. Z, X, and Y. And then, so now, in the new coordinate, we can have R as in radius, and then, theta as in the angle, and Z for height. So radius, but you have to notice for the situation of theta, it's gonna be different because theta is a angle unit. And when we find dt over ds is for distance, we're doing the change in temperature with respect to distance. So we need to convert this to distance, some kind of unit length. So we can have r do to make arc length. So that's how we establish the unit length for this. And then everything else is just dr. dr is expanding of the curve from inside to outside. And then theta is expanding in a angular way, and then z is just expanding up the height. So I'm gonna illustrate the radial coordinates. So it's gonna be z, and then so this is like r, like the radius, and then this is angle theta, and then this arc length RD theta represents the change of arc length with respect to the change of theta. And then when we make an extension over here, we can actually draw a 3D illustration. Right here. My drawing's very bad, but trying my best. Something like this. And so this side's gonna be, and then so DZ is gonna go into this way. So actually this is DR direction, and then DZ is something like this, the height, and then um d theta is over here plus. So this is like the direction, but we're gonna in this question we're gonna talk about heat storage, and this is the direction for the net heat flow. So this is instead gonna be theta, Q theta plus change of theta, like the Taylor approximation that we have worked before. QR plus DR, QR, QZ plus DZ, QZ. So now we're gonna write our energy balance, okay? So we have energy storage is equal to density times heat capacity times change in temperature with respect to times and the volume. So in this cylindrical figure, we established that our control volume is gonna be dr times dz times the arc length rd theta. So we can have this, that's the volume. And then for energy generated, we can have heat flow times the volume dr dz and rd theta. And for the net heat flow, we're gonna work out for each individual direction, okay? So net heat flow, I'm gonna work right on the next page. So for z direction, for example, we can have um energy balance Q in minus Q out. So QZ minus QZ plus DZ is equal to negative. We have done this in our previous homework, so you can go back to the video for reference. So it's gonna be equal to derivative of DZ times negative K A dt over dz times the distance in z. So just delta z or dz. And then, so we know that the area, so let's go back here. So the cross-sectional area is this piece. We use a different color. So this piece with the length, so its length R made up of the arc length r d theta and dr itself, or the radius. So so we know that the area is equal to r d theta times d r, and then we know that this is gonna be equal to second derivative of t times k times r do d theta dr and dz. And then now we're gonna move on to the radial. So this z direction is just actual direction. And then um and then R direction or radial direction, we have the same thing up here. So you have Q R minus QR plus DR equal to negative derivative of dr over negative K A dt dr over dr. So over here we would have the area equal would be equal to, so we're talking about the R direction, so it's gonna be like this. So its area is gonna be made up of um same R, dr, the arc length times the height. So and then we're gonna, so notice here we are this Ka over dt dr is in a bracket parentheses. So this whole thing would be, we would need to find the derivative. It's a derivative of this whole thing. So R is a variable because it's a derivative with respect to R. So R would, we wouldn't be able to move R, but d theta and dz would be constant, so we can move it out. So cancel out the negative ddr k, or we can just move kr out too. So r dt dr dr d theta and dz. And then finally, we talk about the theta direction or tangential. So q theta minus q theta plus d theta is equal to negative d theta over negative k area times dt d theta times d theta. And then over here we would have Ka is equal to R. Also notice here, the temperature gradient for tangential direction, since we can only find the temperature gradient with per unit length, we would have to convert this to dr theta. So finally we would have d theta over negative Ka 1 over r dt d theta. And then r is still a constant, and then times d theta. And then a, we would have r dr times dz. And so we were able to move r and dr over to the other side. So we would have this k, take out the negative, take out k 1 over r dt d theta over d dr, then actually I think I made a mistake. So this one is just simply dr and dz. I'm sorry for that. I was like, what's something's not right. But anyways, and then we have d theta. So now we're gonna write it in a big equation, energy balance equation. Okay, so we would have PC dt temperature respective times dz dr r d theta equal to q dz dr r d theta, and then plus, I'm just gonna pull k out and then factor k out. Okay, so we have k equal to, over here we would cancel out, we would have this second derivative dz squared dr d o r d o, wait, dr dz r d o plus um plus the second one would be d dr over r d r dt dr plus over down here we'd have d dr over 1 r. So since 1 over r is a constant, we're gonna take out in the front anyways. So 1 dt. So yeah, it would be just be a second derivative of d, and then dz dr d theta. Let's move it here. Oops. And then times this for the area too. So this we would have dr, d theta, and dz. And then now we're gonna cancel out all the volume. So we would have cancel out this, cancel out this, cancel out this, cancel out this, cancel out this. But these are both missing an R. So we're gonna have to divide its whole thing by R, each of these two. So rewrite this entire thing would have PC dt equal to Q plus K, the second derivative with respect to Z plus, let's just find the derivative of this. So we would just have 1 over R dr squared r squared plus 1 over r squared second derivative with respect to theta. Okay. And then we move density and heat capacity to the right side. We'd have dT, change temperature with respect to time is to Q over PC over alpha, and then just this equation over here. So yep, that's how we derive this. Thank you for listening. Hi, so we're gonna move on to our second problem. Excuse me. So in this problem, we simplify B1 for the case of steady state with no heat generation and only radial heat flow to yield an expression similar for an equivalent thermal resistant analogous to that in an electrical circuit. So we're gonna draw the situation first, okay? Gonna do, let's do it bigger. It's the outer radius and then inner radius. So RI TI, then ROTO. And then we assume that TI, all these fours are given in our problem. So now first thing first, we write our energy balance equation. So energy storage equal to energy generation plus net heat flow So this is still a radio. So we're gonna use our radio coordinate. We can have R0, wait, R theta and Z. But since the questions say that where there's no heat generation, then only go radial heat flow. So we know 0 and then cross out these two. So and then it's steady state as well. So this one is also 0. So we only have 0 equal to, or yeah, 0 is equal to negative heat flow. Let's see over here. I'm just gonna write the equation that we derived earlier over here. So we have radial over here. Actually, I'm gonna do this. So this one is 0, 0, and we don't have the axial direction or tangential direction. So we end up with this 1 over R, the second derivative temperature with respect to radius, and then we can just cancel out the constant because it's constant, and then we also note that um we cross out because it's constant, so we only have this left. And we're gonna rewrite this a little bit, okay? So we can have 0 equal. So earlier, I'm gonna separate the second derivative into just the one derivative, just a first derivative. So it's gonna be equal to over here, 1 over R is equal to 1 over R derivative ddr over R dt dr. And then we also this R over here is a constant, so we can also eliminate that. So we have 0 is equal to the derivative of R dt dr. So since the derivative of this R dt dr is 0, we know that R dt dr isn't constant because the derivative constant is 0. So let's just call it constant C1. And then we're gonna move, we can do, so we see that this one is a um differential equation, and so we can do method of separable of variables to solve this. So we can have dt over here is equal to 1 over R C1 dr. Or actually, we're gonna solve, we need to solve for C1. So that's what we're gonna do with in terms of T and R. So we can have dt, we're gonna move the R over to the other side. So separation of variables. dt over to 1 over D, 1 over R, C1 dr, and then we integrate both sides. So the upper boundary is going to be the temperature at outer radius, and the lower is temperature at inner radius, and then the outer radius and the inner radius. So we can have over here outer TL over TI equal to C1 over ln R, because it's ln R0 minus ln R naught Ri. So we have this. So therefore we have C1 is equal to TO T naught over T initial minus T initial over ln R naught over Rn inner radius. So now what do we need to do is we need to solve for dt and dr. So we need to find an expression for dt over dr, so then we can plug into our Fourier's law, so we can determine the equivalent thermal resistance. So we would have over here dt over dr is equal to, we have as the expression we write over here, we have r dt dr equal to C1. So therefore dt over dr is C1 over R. And then so we can plug it in our Fourier's law. Q. But I think in this case, we want to find, let's say we want to find a, also, just another note. Once we figure out C1, we can use it. We can find temperature. We can find the expression. We can find temperature or radius at any point. So for example, over here we would have, let's say T dt at any temperature T, and then we can use our inner radius as a reference equal to at any radius R, and then we use our inner radius as a reference over C1, and then we would have C1 1 over R C1 dr 1 over R prime, so like any R that we chose over dr prime over times C times, yep, times C1. So now we're gonna plug this on the Fourier's law, okay? Negative Ka dt dr. So we know that dt dr is 1 C1 over R naught. So now what is A? So A is, so we learned that earlier, when you penetrate through the z direction, our surface area is gonna be the arc length RDO times the radius. And then since we're doing like the entire cylinder, our area is going to be 2 pi times R naught. So the total heat flow, we will have to use the outer radius. So 2 pi R radius times high. High is very important too, because high is Z, and then this thing arc length is theta. So that, which makes the area, because it's flowing through the R direction. Okay. So we would have negative K times 2 pi R naught H is equal to C1 over R naught. So we would have Q2 pi H C1 is equal to negative Q 2 pi H. C1 over here is T outer, T inner over natural log R out R in outer radius over inner radius. So that's Q. So now how do we compare it to analogy to the circuit resistance? So we know that in circuit, delta V is equal to I R, and then in thermal, for thermal equivalence, we have delta temperature driving force equal to Q, the flow or the current times the resistance. So over here, we have delta T is T O over minus Ti, or T outer minus T inner. So rewrite this, we would have delta T Q equal to 2H delta T, and then move this whole thing, whole constant over to the left side. We would have natural log of R outer radius over inner radius over negative. We put negative sign above, so K2A 2 by H times Q equal to delta T. And then we can rearrange, get rid of the negative sign, flip this. So this is the uh thermal resistance for cylindrical shape. Thermal resistance. All right, that's it. Thank you for listening.